Welcome to the 10th class meeting of EECE341, Introduction to Communication Systems. This is a recorded class meeting because we have too many holidays this semester. So in order to meet the school requirement, I need to give you a makeup class meeting. So as far as you do the homework for the 10th class meeting, your class attendance will be automatically regarded as present. Okay, here goes the overview of our entire course. Here, we are spending a lot of time to study Chapter 3, linear modulation techniques. One of the reasons why is that it's so important. So understanding this linear modulation is the key to understand not only this introductory communication systems, but also the next course, digital communications too. By the way, in spring 25, the Department of Electrical Engineering, we will offer introduction to digital communications for undergraduate students. So introduction to digital communications. And this course will assume this introduction to communication systems. So this is, I remember, EECE 441. And 441 has this 341, the current course, Introduction to Communication Systems, as prerequisite. So, and also, I'm going to teach this one next semester. So I will assume that the students are knowledgeable about this linear modulation. Even though in this introductory communication systems course, linear modulation focuses mostly on analog linear communications, linear modulation techniques, but in this introduction to digital communications, we will focus on digital linear modulation techniques, which share linear modulation with analog linear modulation. So this chapter is very, very important. And most of the modulation, modern, current, contemporary digital modulation techniques are linear modulations or little variation of linear modulation. So understanding this topic is so important. Anyway, let's review the previous class meeting number 9, where we started the studying of linear modulation, where our focus was on double sideband suppressed carrier modulation. So let me draw a Venn diagram because it's too confusing without this Venn diagram. So here is modulation techniques. So this is the set of all possible modulation techniques. And here is a very small subset called the subset of all linear modulation techniques. However, in order to make it clear, let me hugely exaggerate its size so that it can take up half of this universal set. So here goes the subset of linear modulation techniques. And the term linear implies the complementary set must be the subset of nonlinear modulation techniques. So this is the big picture. And again, in this subset of linear modulation techniques, there is also a small subset called double sideband modulation. But let me exaggerate again. So let me copy this one. Really copy. Second. So this left subset is the subset of all linear modulations. And here is the subset called double sideband modulation. Got it? Of course, this is very small, probably infinitesimally small subset, but let me again exaggerate. So here is the set of double sideband modulation. And within the subset of double sideband modulations, there is double sideband suppressed carrier modulation. So let me divide it into two. So here, suppressed carrier. So DSB suppressed carrier. Here, suppressed means no carrier. So, and you may say that there is carrier, of course, not that carrier, I mean. You will see after we study double sideband with carrier. So suppressed carrier and with carrier. And inside this with carrier, there is large carrier and large carrier, reduced carrier. So DSB large carrier, DSB reduced carrier. Here reduced means small, but non-zero. Here suppressed means no carrier, additional carrier transmitted. Okay. By the way, some textbook says with carrier as transmitted carrier. So they say that DSB with carrier equals DSB with transmitted carrier. So there are many confusing terminologies, but I hope you have this hierarchy of concepts in your mind. So let me do this. Again, let me use a tree. So here is your modulation techniques, linear, non-linear, and among many linear, you have double sideband modulation techniques, and you have two suppressed carrier, DSB suppressed carrier, and DSB double sideband with carrier or transmitted carrier. And within this double sideband with carrier, there is double sideband reduced carrier, double sideband large carrier. Got it? So I believe this tree is more clear, much more clear than the Venn diagram. Anyway, so I hope you have the idea now. So far, we focused on this one, double sideband suppressed carrier modulation. And what did we learn? Double sideband suppressed carrier was very, how to say that, contains most of the important elements of this double sideband modulation, because we've seen why we need power amplifier in the transmitter, why we need low noise amplifiers in the receiver, why we need in the transmitter local oscillator that generates carrier signal, and why we may need another local oscillator in the receiver to generate demodulation carrier, and we may need RF mixers in the transmitter to up-convert our message signal, or we need an RF mixer to down-convert our received signal to real baseband, something like that. And also, we've seen the block diagram of a simple receiver that was called phase coherent demodulator that performs coherent demodulation. Sometimes we just remove phase. So simply coherent, non-coherent demodulator and demodulation. And there, what was the pros, which means that in Korean 장점, and the phase coherent demodulator had a very simple structure mathematically or theoretically. Why? Because as far as you can find out the phase angle of the received signal, then you regenerate the same demodulation carrier and multiply it to the received signal. And from a trigonometric identity, cosine square theta equals 1/2 1 plus cosine 2 theta divided by 2. Then by low pass filtering, after you multiply the modulation carrier, then you have the message signal. So ideally, the receiver could be very, very simple. But what was the problem? I mentioned that in the early stage of radio communication, it was not easy to even generate a very good, stable carrier signal. So usually they had this some data of t term, which is far from constant, right? So this data of t may even contain some carrier frequency offset, which I emphasized, and this makes our receiver perform very poorly if we just assume our receiver has phase coherence. But actually it does not. Then performance degrades a lot. Then how can we solve this poor RF components performance in the old age? So engineers always do trade-off whenever they have they first consider trade-off research or trade-off type problem solving whenever they have a problem. And actually that was the approach. So first, they consider putting more complexity in the receiver by using so-called phase-locked loop, PLL. And one of the interesting phase-locked loops is the Costas phase-locked loop, which can find the, not only find the frequency, but also, let me simply put, that can simply almost robustly recover the instantaneous phase angle of the received signal if the signal is double sideband suppressed carrier signal, or later it could be extended to double sideband with carrier. Anyway, so the Costas PLL can be employed in the receiver to improve the performance of the receiver, even if we have very poor, relatively poor local oscillator that generates demodulation carrier. But as I told you, it was very costly and not that practical in the early stage of radio communication. Another one is using the squaring device based phase lock loop. And suppose you have some cosine 2 pi FCT plus some theta, and it is squared. Then what do you have? Again, you have 1/2 1 times cosine 2 pi FCT plus theta times 2 here. And usually this type of thing makes phase ambiguity, because you can add here 2 pi n, and if you divide this entire thing, what happens? You have 2 pi FCT plus theta plus now n pi with some integer n. Means that after you square the received signal and try to extract the phase angle information, you may have some 180-degree ambiguity at the output. Of course, in a lucky situation, you may have integer multiple of 2 pi, but you may have odd number n. In that case, your message may have polarity change. However, as I told you, if our original message signal for the DSB-SC modulation was, for example, acoustic signal or speech signal, then our ear cannot distinguish the message M of t and negative M of t. In that case, this polarity change, because cosine something plus pi gives you negative cosine b, right? This polarity change doesn't matter. So that's why in some receiver for DSB-SC, they use the squaring device-based phase lock loop. Anyway, such a kind of phase lock loop, whether it is Costas phase lock loop that finds the exact phase angle of the received signal, or the phase angle of the received signal with possible 180-degree ambiguity, these PLLs are relatively cost inefficient at the time. So engineers traded off what the actually transmission power efficiency with the receiver complexity. So it's like you have a scale in Korean, 저울, where you can spend something more in the receiver like this, or you can spend something more in the transmitter, like what we are going to study today, double sideband with large carrier. Okay, sometimes this double sideband with large carrier is simply said amplitude modulation, and this is also very confusing, because if you remember, any real valued bandpass signal can be rewritten as, after proper choice of carrier frequency, some amplitude times cosine 2 pi fct plus theta of t, where we call this the amplitude. And we already know double sideband suppressed carrier is only changing this part with fixing theta of t as a constant. In that sense, double sideband suppressed carrier does modulating the amplitude only. So according to our common sense, DSB-SC must be a subset of amplitude modulation if we want to define the terminology amplitude modulation. However, due to the historical reason, AM, which obviously stands for amplitude modulation, usually does not mean DSB family. It only means double sideband with large carrier. So very, you should be careful, okay? Anyway, so today's topic is double sideband with large carrier, which is often or almost unanimously named amplitude modulation. So let's see. And here the preview just summarizes the hierarchy I mentioned. So within linear modulation, within the subset of linear modulation, we have double sideband modulation, and inside we have double sideband suppressed carrier. Here suppressed means no additional subcarrier. The antonym is double sideband with carrier or double sideband with transmitted carrier. So these are complementary sets. And today we are going to study this one, double sideband with large carrier. Okay. And the key terminologies you must understand is modulation index. Okay, and this enables envelope detection that performs envelope. So envelope detection performed by envelope detector. So if I draw a block diagram with acronym ED, what does that mean? Here is an envelope detector. And I will define it later in today's class meeting. As I just told you, the double sideband suppressed carrier had the cones, which means that 단점들 in Korean. So they wanted to trade off this problem by increasing something bad in the transmitter, and that was power efficiency. So I will explain later in today's class, but I hope you remember this one. Double sideband suppressed carrier, if we want the receiver work properly at the early stage of radio communication, it was so cost inefficient. So it was very costly. In order to make the receiver simple, engineers decided to make the power efficiency at the transmitter decrease. So they sacrificed power efficiency at the transmitter. So transmitter wastes a lot of power. However, by doing so, the receiver complexity could be amazingly decreased by employing so-called very simple envelope detectors. Got it? So that is the idea. As an engineer, you always have to remember this one. Whenever you have a problem, the simplest approach is to do some trade-off. Once I told you within this course that one of the most good inventions in history did what? They had the scarce resource, and they replaced the scarce resource with an abundant resource. That was one of the keys for great inventions. Same thing happens here. Mathematically speaking, the DSB-SC is perfect, very good. Not completely perfect, but in terms of power efficiency, very, very good. However, at their age, the receiver complexity could not be tolerable for most of the radio receivers. So they sacrificed power efficiency at the transmitter to make the receiver complexity reduced and the receiver affordable for many people. Got it? And that kind of trade-off occurs again and again. We will see something called the single sideband modulation, probably not today's class meeting, but in the next class meeting. And of course, this single sideband modulation tries to improve double sideband modulation. And always, if there is pros, there is cons. So they have some compromise. And then they have something in between single sideband modulation and double sideband modulation, which is named as vestigial sideband modulation. And it has pros and it has cons. And it was in the early stage of television broadcasting, it was a very good trade-off. That's why VSB was employed by the analog TV broadcasting. By the way, there is so-called the digital VSB. So the digital vestigial sideband modulation. And actually, this is employed by digital broadcast TV, digital TV broadcasting. Anyway, probably in the next class meeting, I will talk about VSB. Okay, here goes the amplitude modulation. And academically speaking, this is what? This is double sideband modulation with large carrier. Okay, and as you know, this kind of adjective in Korean, 형용사, is very vague in academic sense, right? Every adjective, 형용사, is actually a relative one, not absolute definition. So anything can be very large and anything can be very small compared to something other, right? So what does this mean? In order to make it precise, we introduce the notion of the modulation index of the AM. By the way, there are other modulation indices for other modulations. So you'd better say this modulation index as the modulation index of the amplitude modulation. And here goes the transmitted signal. So this is the real bandpass signal that models the signal applied to your transmit antenna. Got it? So you have the transmit antenna that converts the electrical signal to a radio wave. And of course, there is a power amplifier, but let's say that this signal, XC of t, is the electrical signal applied at this point. Got it? And as usual, as the DSB-SC, we have carrier. Of course, here, this carrier may have some constant phase, but for simplicity, this phase is ignored, okay? Precisely speaking, there should be phase data, unknown, non-random phase data. Or even due to the non-perfectness of our local oscillator, we may have time varying, hopefully slowly time varying data of t. But anyway, let's ignore that for simplicity, right? So let's make the simple to keep the essence of the problem. And here goes a constant. Okay, that doesn't matter. Anyway, we are going to hugely amplify the transmit power and apply it to the antenna. And so this is the core. This is the most important part in the amplitude modulation, which academically speaking, DSB with large carrier. And before we talk about what is A and what is M sub N, let's expand this one first. Okay. So where it is? Okay, let me just expand it because it's not that difficult. So XC of t after the expansion is what? A sub C amplitude of carrier, they probably also wanted to mean, times cosine 2 pi fct plus amplitude of carrier times A, the modulation index of this AM modulator, M sub N of t cosine 2 pi fct. So let's focus on the first term of this signal applied to the antenna and transmitted. Okay. What is this one? Yeah, this is a carrier signal, right? Why? Because suppose message is 0. By the way, message is M of t and M sub N of t is proportional to the message. So if M of t, the message signal is 0, then this M sub N of t, actually minimum normalized signal. So this N means normalized. Normalized means that the something is set to 1, the unity, okay? And normalization depends on what is normalized, but I will talk about it soon. Anyway, so by this definition, message 0 means normalized message signal is also 0, and the second term disappears. In that sense, the signal applied to the amplifier, power amplifier in the transmitter or receiver, or you may just view that transmitted signal to make everything simple. Then transmitted signal is just a carrier signal, and carrier without time varying amplitude or time varying phase angle, actually phase deviation, precisely speaking, because we want to remove, we do not want to take this 2 pi fct as a time varying phase. Anyway, this is message independent and message independent, so no information. And this is a carrier signal. So that's why we say that this type of modulation is double sideband with carrier or double sideband with transmitted carrier. Got it? Then you may say that, wait a minute, professor, you just said that this is the signal model for AM. And actually, additional constraint to this model makes this signal DSB with large carrier. And here, this is the constraint. Okay, here if A is chosen as a number between 0 and 1 can be chosen, but anyway, then this is called so this makes this signal DSB with large carrier. And if we only have that one, we may say that DSB with carrier or DSB with transmitted carrier. Got it? And so this one is the key to understand the difference between general double sideband with large double sideband with transmit carrier from it's a smaller subset of double sideband with large carrier or simply AM. So here I have drawn a figure of message signal. So consider this is the time axis and this is your message M of t. And it may vary in time domain, taking some positive values and some negative values. And here, as you see, we find the minimum value of this message signal. It could be positive or negative, but since in AM modulation, acoustic signal converted to electrical signal is so important, including speech signal. And these signals usually takes positive value or negative value at the same time. So let me draw it this way. And here is the minimum of M of t, and which is intentionally chosen non-zero. And what it do is like this. So M of t, the message signal is greater than or equal to the minimum of M of t, right? It's obvious because the minimum is the minimum. And we have this simple manipulation that gives us the understanding of that modulation index. So let me show you. Okay. Computer is not working. Just a sec. Okay, I hope now. Yeah, okay, it works. So this part is very important. So let me mark it. Okay, so we started from our message signal that could be positive and negative. So we find the minimum of M of t. Usually it's negative value. And now let's move the right-hand side term to the left-hand side by subtracting the same thing. Then we have something like this. Or you may just keep going from this first line. And what we do is that we divide the both sides by absolute value of minimum of M of t, assuming the minimum value is non-zero. Then what happens? Since minimum is defined as a positive number, this direction of the inequality does not change, right? Or let me just do this, right? Because it would be simpler. So let me just delete this one. So we have started from M of t is lower bounded by minimum of M of t. And we divide both sides with non-zero value, absolute value of minimum M of t. Now, what is the right-hand side? Right-hand side is in general 1 or -1, depending on whether M of t can, a minimum of N of t can be negative and M of t can be positive or something. But since something is divided by its absolute value, this value is either 1 or -1. So you can easily see that left-hand side is either greater than or equal to 1 or greater than or equal to -1. What does that mean? This means this left-hand side is greater than or equal to -1. If it's greater than 1, it's obviously greater than 1 equal to -1. And this left-hand side is defined as the normalized version of the message signal in our definition of amplitude modulation, alias DSB large carrier. Got it? So we now have this one. So far, so good. Now we introduce the modulation index of AM, which is to be multiplied to both sides of this one, and it will be chosen as a non-negative value. So you multiply A, which is positive. Okay? Then what happens? Since a positive value is multiplied, what happens? This direction of the inequality doesn't change, and you have this. Right? So under the assumption of A positive, these two are the same, right? So A times the normalized message signal M sub n of t is greater than or equal to -A. Now you add 1, and you may say, why? But anyway, let's add 1, and let's see what's going on. If A is chosen not only positive, but also less than or equal to 1, what happens? The right-hand side becomes 1 minus A, and which becomes strictly, non-negative, right? If A is chosen, the AM modulation index is chosen less than or equal to 1 and greater than 0. So this value that appears here, right, in the definition of our AM modulated signal is always non-negative. Got it? Okay. This is the key. I know you got a lot confused if you see this definition of AM modulation first. Okay? And I also had that same confusion when I was at your age and taking this introduction to communication system. Okay, but anyway, so let me just put a space because it's so crowded here. So it is so slow. Sorry about that. Okay. So okay. So let me repeat the definition. It's so important. So definition of AM, amplitude modulated signal. Okay. So x of t or x sub c of t equals what? Some constant times 1 plus the modulation index of AM times the normalized message signal times carrier. Okay? You may put some plus theta, but it doesn't matter. Okay? For just for convenience, let's say theta equals 0. And here, A is less than or equal to 1 and greater than 0. Okay, and Mn sub t is defined as the message signal divided by the absolute value of its minimum. And what does this two conditions mean is this. So we start from minimum, M of t is greater than or equal to its minimum. And assuming that minimum is non-zero, we divide both sides with absolute value of the minimum. Then this is greater than or equal to -1 always. Now we multiply A to both sides, assuming A is positive. Ready? And we add 1 to both sides. And we put one restriction. What? This is less than or equal to 1. What does that mean? 1 minus A greater than or equal to 0. So we have this is greater than or equal to 0. What does that mean? As I just mentioned, this part is always greater than or equal to 0. Actually, the restriction that after we defined normalized message signal, A is positive and less than or equal to 1 makes this factor non-negative for all t. Got it? This is the amplitude modulation or DSB with large carrier. The reason why this is called large carrier will become obvious after we carefully study this modulated signal in the time domain and also in the frequency domain. So let's move to the next part. Okay, so we've just covered this first bullet. Okay? And you may say that, wait a minute, why you are so slow in covering the course? As I told you, this part is so important. And if I just cover very fast, more than half of you will never understand the amplitude modulation. So that's why I'm covering very, very slowly. Okay, so we will cover it later, but if we move from double sideband without carrier, additional carrier, which means double side suppressed carrier, to double side band modulation with large carrier, then there is of course, pros, 장점들. Otherwise, we will not move from DSB-SC to DSB-LC. And the most important thing is that at the receiver, so at the receiver, we can perform envelope detection. And this envelope detection could be performed by a device called envelope detector, actually, which is a circuitry that performs this mathematical operation. And this could be built very, very simply. Got it? So that's why we human beings started radio broadcasting employing amplitude modulation, the amplitude modulation. So many applications in commercial radio. Before we talk more about the demodulation, let's focus on the modulation part. So here goes the time domain representation of AM signal, or you may say that AM at TX, at the transmitter. So this is the message signal exemplary, okay? Message signal could be other waveform. Suppose this is our message signal, and it starts from 0, and it looks like that, suppose, okay? And the modulator output, so let's say this is the AM modulator, amplitude modulation modulator. But anyway, AM modulator. Then, okay, sorry. Yeah. We must say input is M of T, and here is the scaling, right? So we have the input message signal, right? It could be positive, it could be negative at some time instant. And suppose mathematically we can find the absolute value of minimum of M of T. And first we divide it divide the message signal by this absolute value of the minimum, and it becomes the normalized message signal. Now, what was the next step? We amplify. We multiply the AM modulation index, A. And this AM modulation index is positive and less than or equal to 1. So here, this amplifier or multiplier output is A times the modulation index times the normalized message signal. Now, what you do is that this, by the way, this sigma can be replaced by this plus. Got it? It's an adder. And don't ask me how to build a circuit that performs adder. You learned in circuits course. You can use, for example, operational amplifier to build such an adder. Anyway, so here is actually 1 means 1 for all t. It's a constant time function. So you add the signal constant. So you have 1 plus the modulation index of AM times the normalized message signal. And what is this one? This is a modulation carrier, or simply carrier, generated by a local oscillator. So local oscillator generates this signal. And here, this multiplier is not just a multiplier. It's usually called an RF mixer. And then you have this signal to be applied possibly to a power amplifier connected to the antenna, transmit antenna. Got it? So here, this XC of t is this one. Got it? And see carefully. This part gives us the minimum value of the message signal, right? And after our careful definition of the normalized message signal and modulation index, you can show that this minimum value, as far as A satisfies this one, is always appears on the this positive part if you draw the envelope of the signal. Okay, so see that this part is here, that part is there. Got it? So after AM modulation, the transmitted signal looks like a carrier signal that conveys the message signal in its envelope. By the way, even though this is just called envelope, the definition of envelope is different. Okay, this is not a good definition of envelope. Actually, the definition of envelope, precisely speaking, is what? Given a real valued bandpass signal, you have a complex envelope, and the absolute value of the complex envelope is called the envelope. Now, what it is? You can rewrite, see that? XC of t, which is complex signal, is the envelope times e to the j some angle. Got it? So you can rewrite x of t as xc of t times cosine 2 pi fct plus some angle of t. Now, what if this is a constant? If constant, what happens? You have unmodulated carrier where the deviation is magnitude defined this envelope. Got it? So this is actually an envelope. Okay. So this is the definition of envelope, and you can now say that amplitude modulator, AM modulator, let the carrier let the carrier convey the message signal in its envelope. Let the modulated carrier convey its message in its envelope. Okay? And also, when the envelope becomes minimum, this envelope becomes minimum, the message becomes the minimum value. Or if the message becomes minimum value, envelope becomes the minimum value. Got it? That is the AM modulator and or AM modulation. Got it? So this is the figures you have to be able to draw. For example, I may give you a exam problem saying that, okay, draw a block diagram of an AM modulator. And not only this just to see, but also I hope you must be able to put M of T and this scaling multiplier, because this is the complete AM modulator. Got it? In your answer. That's what I hope. And if you are very precise, then probably you want to add some constant data too in this phase angle of the carrier. Got it? So do you understand what I mean? If the message is, for example, something like this, then what would be the modulator output? Modulator output would be, so this is message, let's say A, negative half A, okay? Then you will see something like, so the envelope follows this message signal, and you have some oscillation between this envelope, okay? Roughly speaking. Got it? And by the way, whenever you have inequality, usually we consider the extremes, like what if A is very close to 0? What if A is very close to 1? That's what you are going to see, okay? So let's go back to our formula. So first, what happens if A is very small? Which means that normalized message is very small relative to this constant 1. Got it? So envelope variation would be relatively smaller. What if A is close to 1? That is answered here. So if A is close to 1 or 1, what happens? You may have this term, this value, 0. So actually, this part where you have minimum value of message may touch the time axis. So this is A greater than 0, less than 1, and here A equals 1. Then what would you expect? You have something like this. And there will be no signal here, and the signal there. Got it? So if the modulation index becomes smaller, then you have more carrier component and small amplitude modulated component. If A becomes close to 1, you may have some 0 carrier here. Got it? That's the idea. So you have to be able to draw, sketch the AM modulator output given the value of A. Okay. Now, before we talk about the transmitted signal in the frequency domain, let's see how to demodulate this AM signal using so-called envelope detector. So the idea is like this. In the receiver, what is this signal? How can we model this signal? Let's say this signal is modeled as a continuous time function y of t. And let me say that gain and some signal amplitude AM, M, N, or let me ignore the delay and let me just have some unknown phase here, okay? Now, we know that if we can build some system called envelope detector, which extracts the envelope of this signal. So envelope detector on envelope detector is a device by definition that extracts, or in this case, detects the envelope of a real valued bandpass signal input, or an input real valued bandpass signal. Okay, then what would be this output of the envelope detector? Envelope detector would be what? So let's find the complex envelope first. And it's not that difficult because we know what is the Euler's identity and how can we combine Euler's identity with this real part operator. So let me copy e to the j theta, e to the j 2 pi fct. You may also say that there was some, let me forget about it. Okay, so what is the complex envelope of this signal? This is the complex envelope, right? So envelope detector mathematically view the received bandpass signal as the real part of the complex envelope times e to the j 2 pi fct, right? So the output would be what? Simply absolute value of this one. So GAC 1 plus A mn of t done, right? Because e to the j theta has absolute value 1. Now, is this proportional to m of t? And now we know that if A is greater than 0 and less than or equal to 1, then actually we have what? No, sorry, not this one. So this one equals what? If A is greater than 0 and less than or equal to 1, it's positive, non-negative. So we have mn of t. And now here is a filter that blocks DC. So there goes a DC block filter, which means that this GAC plus GACA mn of t. And this is blocked. Then we have what? Now eventually we have something here that is proportional to this second term, which is again proportional to the message. So this is the idea of the envelope detection. So envelope detection of amplitude modulated signal. You use amplitude detector followed by a DC blocking filter. Then you can recover the a constant multiple of the message signal. Of course, it could be delayed. Got it? Now, how can we build this one? This part is not that difficult. You learned in signal gen systems how to build a DC block filter. It's actually notch filter that notches out the DC component, right? So it could be simply built using a capacitor because capacitor blocks the DC component. Okay. Anyway, so how can you build envelope detector? And it seems that according to the mathematics, it's not that simple. Okay, we want to build some system that does this mathematical operation, right? You have a received signal. Somehow you convert this real valued bandpass signal in this form, and you identify this is the complex envelope part, and you take the absolute value of modulus. Where can you build a circuit that does this mathematical operation? Probably very, very difficult. However, a circuit that does this operation approximately can be made very, very simple and cost effectively. That's actually the history. So let me show you an amazingly simple envelope detector, and you learned it in your circuits course already. And here is the detector. So this is, let me say, a practical envelope detector, okay, that performs an approximate envelope detection. Okay, so this is the power of cooperation between the left building and right building of electrical engineering twin tower. Okay, so theoreticians think about what kind of mathematical operation is useful. It does something wonderful. And on the right-hand side building, electrical engineers devise the systems that performs such a mathematical or logical operations. And our culture evolves. Got it? So here is a diode, which is a nonlinear device, and we have a RC circuit. And as you know, if this input signal to this two-terminal system has the voltage goes up to the positive part, what happens? This diode turns on and the current flows both of the sides, mostly this to the diode if R is very large. So what happens? During this positive part, the electrical charges are stored in the capacitor. And what happens in this negative cycle? This blocks. So this becomes open circuit, and the charges stored in the capacitor flows through the resistor. Got it? So we see the time decaying voltage. So now let's see. What if the input to the envelope detector is this AM signal? So we have some envelope over carrier. So we have a lot of oscillations here, right? So this is now applied to this input. What happens? If the signal goes up, the capacitor is charged, and if the signal goes down, what happens? There is an RC time constant, right, that holds this voltage. And before this goes down, what happens? Signal goes up again. And what do you have? You have some signal output that roughly, approximately tracks this envelope of the signal. Got it? By the way, this B is the signal at here. Okay. So this is the B, right? After the diode. But anyway, so you have the approximate envelope. Okay. However, as figure C shows that if depending on the RC time constant, so relative value of this product, when the envelope goes down, the envelope detector may not follow the envelope, or it may decay too fast. So you need to choose the RC constant, time constant carefully, but at least, let me draw it here. In this cycle, you have some not too much varying signal. The time constant is short, then it goes down, goes up, goes down, goes up, and you have the envelope. Got it? And now we need a modification here because it's a practical envelope detector. So practical envelope detector based on the diode and RC. What do we need? We need probably low pass filter because we want to remove this kind of zigzag, very fast varying component. So this would serve as approximate envelope detector. Okay, so this is, let me say, this is what? Diode. Okay. Got it? So diode, you may say that it's a semiconductor. No. Actually, a diode could be built without using semiconductor technology. So it could be built using other techniques in the early stage of radio communication. So R and C was well known, and some nonlinear rectifying device could be built at that time. So this was the approximate envelope detector that approximately does this mathematical ideal operation. Got it? Now, let's go back to the transmitter part again. So now you know what is good with amplitude modulation. What is good with amplitude modulation? It enables the practical, very cost-efficient receiver possible. Got it? So in the receiver side, it's very good. So AM has one pros. So cost effective RX. Then always pros comes with cons. In Korean, 단점들. What would be cons? The first most important is power efficiency. So in the transmitter wastes a lot of power. And let's see. So this is the notation in our textbook, and actually it's almost standard in electrical engineering to calculate the average power of the signal. So here, this bracket means compute the average power of what? Of the signal here, which is usually a time function. And what is a time function? Time function is the AM signal squared. Okay? So what is that? Some signal squared time averaged. This is what? This is average power. The time averaged power. So average power of the AM signal. Now our objective is to see the power efficiency. So this is the kind of total power. And what is the signal part of the transmitted signal? So what we do is that we've seen already in our signal model, where it is, I have written down somewhere. Let me just mention it again. So we have what? We have xc of t that equals to AC cosine 2 pi fct plus AC A mn of t cosine 2 pi fct. Got it? So this part conveys the message signal. So what you want to know is that among the total average power, what is the power of this message conveying signal? Got it? So we compute the denominator first, and here it goes. So we expand the AM signal, and assuming that the mean value of the message signal is negligible or 0. What does that mean? As I told you, if the our message signal is an acoustic signal converted to electrical signal or voice signal, it's almost right. It's almost symmetric with respect to time axis. So if we have something goes up, we have almost the same thing goes down. Of course, it does not happen at the same time, but it is very close, right? So people have found the DC component is almost 0 in our in the acoustic or speech signal converted to electrical signal. So here we have some cross terms like this, and we ignore this. But then we have what in the denominator? What is this one? This is the actually power of this carrier. And this is what? This is the power of the message carrying part. So actually, this ratio can be simply written as sum of these two in the denominator and the second term in the numerator. And let's delete some common parts, right? And then you can easily show that the ratio is simply what? A squared times the average power of the normalized message signal that appears here, divided by 1 plus that value. And here, what is our assumption? A is greater than 0 and less than or equal to 1. What does that mean? Actually, this is non-negative, that is non-negative, and A squared is non-negative, so we can easily show that this is less than 1. So power efficiency is not 100%, and it's okay. And when the efficiency, so total transmitted power, and among which what is the message carrying part? So we want this power efficiency close to 1. And that happens only when A squared is very, very large. So limit A tends to infinity, the efficiency converges to 1. Now, what happens if A cannot be made sufficiently large as in our definition of the AM modulation index? Then we have inefficiency. And here goes some simple examples. So we assume that the message signal M of t has a symmetrical maximum minimum value. This is not the academically well mathematically defined one, but let me just say that if it goes up, then within a few microseconds, it goes down, and this part is almost same, and so you have almost 0 instantly on average. Got it? Something like that. Okay. Then you can show that the average power of the normalized message is less than 1. It's not that difficult because max and mean has the same absolute value. Okay. And due to the assumption or definition of our AM modulation index, then, for example, we have a square wave or sinusoidal signal, we can easily show that the power efficiency is just half. Actually, maximum is half. So when A equals 1, we have, so this is M of t, and if this is square, then you've already seen that transmitted AM signal, be precise. Looks like that, and we have power efficiency which cannot exceed 50%. You can easily show that. Okay. Just a second. I'm sorry. If M is square wave, then 50% power efficiency. If it is sinusoidal signal, we have additional power inefficiency. So in sinusoidal signal, we have maximum 33.3%. Okay. Of course, if A is very large, efficiency can be 100. The problem is that it violates this A greater than 1 violates our assumption of AM, definition of AM modulation. In that case, we cannot use envelope detection. And you may say, why? And let's see. Here goes the case where we have a slowly varying sinusoidal message signal. Got it? So message signal is something like this. Okay? So M of t is here. And now you use modulation index 0.5, 1, and you violate. And let's see what happens. And as you know that in this case of the extreme case, this minimum value translates to what? This one. Okay. So it touches 0. Now, it can be easily shown that if A is greater than 1, that your minimum actually goes down, and if it is multiplied by sinusoidal signal, you have this envelope. So your message has this signal, but unlike the AM modulated signal, that gives you proper envelope. Now you have incorrect envelope here at this point. So you cannot just make the power efficiency greater than 1/2 easily by violating the assumption of AM modulation, because you want to have simple, very cost-efficient envelope detector in your receiver. Got it? So this is not allowed in envelope detection of AM signal. And here goes more quantitative example, because this is so qualitative. So for convenience of analysis, let's assume our message signal has 2 sinusoidal components and looks like this one. And here goes the minimum value. So M of t is negative 4.364 at time frequency product 0.435. And also we can compute the average power of the normalized message signal as 0.5215251. And you can show that when A equals the modulation index 0.5, we have power efficiency just above 10%. Got it? So AM in general, you can say that it's not power efficient at the transmitter, but that power efficiency is sacrificed for the ease of demodulation by employing simple, very simple, cost-efficient envelope detector. Got it? So that is the idea. By the way, about conjugate symmetry, I talked a lot, and you may say that, okay, this slide seems misplaced, but actually it is not. we are going to, in the next class meeting, so-called the SSB, the single sideband modulation, and this conjugate symmetry of what? The Fourier transform of a real valued signal comes again. So from the beginning of this course, I said that signals and systems is the prerequisite and very important. And one of the most important result is that if you have a real valued signal, its Fourier transform satisfies what? Conjugate symmetry. This comes up again and again and again, as you will see in the next class meeting. That's all for today's class meeting, and there will be, again, homework 10, which is due on next Monday. That's all for today.